Hello, everyone. Thanks a lot for being here today. I know we are very close to the Christmas break, so I know it's you are ready for lunch, dinner, and traveling. So we are very happy to have you here. So this is the last seminar of the year. So overall, we are very happy this year because we have been able to organize for each month of the year one seminar, and we are very excited to this series of event, and this continue also for the next year. As usual, if you think you have something to present, please contact me, Satoshi and Leeds, and we're very happy to have you on board. So today we have excited of having Danni Liu, who is she is a PhD student at Karlsruhe Institute of Technology in Germany, and she will present her work on learning share representation for translation in low resource condition. So then, as usual, you know the format. You have 45 minutes to present, and then we have questions. And if I do well, I mean, we have limited group of participants. So if you have questions, feel free to raise your hand or talk, and we also during the presentation, so we can make this more interactive. So the stage is yours, and thanks a lot for being here today.
Thank you. Thank you. It's great to be here to talk a little bit about learning shared representations for translation in low resource conditions. So my name is Danni Liu, and in this presentation, there are also slides from my colleague Tuan Din. And of course, we got a lot of feedback and help from our PhD advisor, Jan Nihus. So speech translation in general, I guess there are two paradigms. That is the cascaded paradigm, where we are first transcribing into text and then doing translation again. And there's also the end-to-end paradigm, where we have one model where all the parameters are jointly trained for the speech translation task. So although I guess often we say that the end-to-end situation is more vulnerable to data scarcity, basically not having enough paired data. But actually, for all these more data-driven approaches, when we have little training data, it's in general bad news, because we won't have as good performance. Performance will be unstable, and all these are horror stories. So this is where I will try to focus on today, low resource conditions where we have little training data. Also, as we have seen in past IWSLT tracks, the low resource track is also one of the very difficult ones, where some strong methods from like high resource pairs like English, German don't necessarily help there. So I think it's a quite relevant question to ask, what can we do to improve translation quality in this kind of conditions? And more specifically, our focus is on if we can try to encourage some kind of shared representation across tasks or across languages in order to get this kind of improvement. Right. So if for today, I'll first, in the first part, I will focus a little bit on like learning language independent representations for text to text machine translation. So this is more a component in the cascaded approach if we consider the speech translation pipeline. And there we'll focus especially on zero-shot translation. And in the second part, I'll focus on our effort on trying to reduce the text and audio modality difference more for the end-to-end regime here. So first, let's go into the first part. Yeah, it's about multilingual translation. It's about language diversity. We know that there are like 7,000 languages in the world, and to handle all these languages or a part of these languages, it's quite useful to have a multilingual translation system that can do many pairs. So there are at least, I see two benefits. The first is that it's easier to deploy, that we don't have to build models for each translation direction. And especially in speech translation, if we already have like an upstream ASR system, it's even better to have one encapsulated component just for multilingual translation. And the second benefit is that there's the possibility of sharing knowledge or learning some knowledge that is shared across languages. So to extract this kind of common features or shared knowledge between languages, actually there are efforts from quite long back. So there are these constructed languages like Esperanto. These are good examples of this. So with the current neural machine translation systems in mind, what we want to ask ourselves is that, can we also do something similar? Can we adapt our current neural machine translation system to also learn something like an artificial language, artificial constructed language like Esperanto, and also in doing so increase the cross-lingual knowledge sharing and then improve the performance in very low resource conditions? Right. So a really good thing about these constructed languages is that there are less translation directions to learn. So suppose that we have a source speaker that already knows how to speak the artificial language, and then the target speaker also understands this language. Then they no longer have to kind of learn each other's language to communicate with each other, right? So it's kind of computationally, it's also attractive in the sense that we are now reducing the quadratic number of translation pairs down to linear. And this also mirrors a situation when we train models. Excuse me. So there are also these conditions where we don't have direct parallel data for training the models. And for example, here, so we know that already there's quite some evidence that our current multilingual models are able to do some zero-shot direction translation of directions that the model has never seen in training. However, what is often the case is that the direct zero-shot inference is often unstable. It's vulnerable to many conditions in training. So quite often, currently pivoting like into translating into an intermediate language and then out of it again is often still a quite strong performance upper bound. Now, if we contrast these two conditions, like the pivoting versus the direct zero-shot translation, we see that there's one difference. One difference is that when we are doing pivoting, we are pivoting through some discrete tokens, as in that we are representing the intermediate into some discrete tokens and then translating again. So now this is what motivated us to learn this kind of artificial language in order to simulate the situation in pivoting. Right. So actually, representing the sentences as discrete intermediate tokens also has an interesting byproduct. That is, it's a tool for analyzing the model representation. So although in the literature, there are already several methods for analyzing the hidden representations of multilingual neural machine translation models, they often involve some kind of heavy post-processing before we can actually see the results. So we have to do some additional training or post-processing on top of a trained model. But then if now we have our input sentences all mapped to some list of discrete tokens, then this interpretation or investigation of the hidden representation also becomes easier. Now, with all these potential benefits in mind, let's move on to the method. So what we want to have essentially is a discretization module. now let's first consider the standard encoder-decoder model. Here we have the input tokens encoded into context, and the context vectors are more or less points in a continuous space. What we want to do is to add this discretization module here that restricts the variety of the variety of points in the continuous space for representing the context. Let's say like for here, for this H3, let's say it's mapped, after discretization is mapped to this point, other point in the nearby H3 prime. But what is actually important here is that when there are other similar states coming later, HI or HJ, they should also get mapped to the same point H3 prime. And in this way, we're hopefully giving the model a bit more capability of learning something that is common and shared. Right, so how we achieve this is that basically we now add a code book in between. And this is essentially a new embedding table with K entries, K being the vocabulary size for the code book. And now the input, so what comes out of the encoder will get mapped to some entry in the code book by a nearest neighbor lookup. And then for the decoder, it'll see the discretized context. So this is the rough idea of what we wanna achieve. However, there are several challenges on the way. So the first is how do we do end-to-end training in this case? So recall that here when we are doing the nearest neighbor lookup, we are returning indices in the code book. So we get a bunch of indices, but this operation is not really differentiable itself. So here, luckily, we could follow the idea of vector quantized variational autoencoder. So first, what we do is this straight-through estimator, which essentially copies the gradient from the post-discretization components onto the pre-discretization components. So this way, we still allow gradient flow to the bottommost parameters, which otherwise will not receive gradients. And also to have this gradient estimation meaningful, we also reduce the distance between the orange and blue blob in the sense that we push them closer to each other. So with this, we can do end-to-end training, but the second challenge is more related to capacity. So here, this discretization module is more like an information bottleneck in a way. So it, in a way, limits how much the model could learn. So what we do to kind of walk around this a little bit is to have a soft discretization and training, in the sense that now the decoder is not only seeing the discretized context from the yellow part, but also by some probability it's able to access the richer and more informational context prior to the discretization. So basically, by training like this, we assume, and we also verified that when the model converged, the context will be relatively well clustered. So at inference time, we are still using the blue blob here, so the continuous context for inference. Right. So then the third challenge is this so-called index collapse. This happens when this nearest neighbor lookup here returns only one or very few entries out of the codebook. And this is very bad. This is very bad for the decoder, because then the context that it receives will be basically meaningless. So here, how to counteract this is that we do so-called slicing that was originally proposed for autoencoding tasks as well. So what happens here is that we slice up the hidden dimension of the context, and for each of the slices, we are doing one nearest neighbor lookup out of the codebook. So the result is that each of the input tokens will then be represented by multiple codes. Now, with all of these, we are ready to move on to put our method to test. So
Sorry, Dan, I have a couple of questions, if
yeah,
I
please go
may.
ahead.
Can you go back? So the
Yeah.
first thing is, what's happen if when you use the nearest neighbor and what you retrieve is very far away from HI? So do you consider the distance? Because probably with the nearest neighbor, you can always find something in E
Mm-hmm.
to select. But if it is very far away from H1, so it means that you are collapsing something to something which is not probably related to it.
I see, I see. It's definitely a good point. So I guess the question is it even meaningful to um use a neighbor that is not really a neighbor in the space?
Exactly. That's the point. Yeah.
Yeah, so definitely at the beginning of training, this is so we don't really consider the scale of the distance, but since here we also have a mechanism that shrinks the distance between, so these are between the neighbors and the actual points themselves. It's a mechanism like throughout the training to push this distance smaller and smaller.
Okay.
So definitely at the beginning of training, we are gonna probably end up with some faraway neighbor, but we do have a mechanism to reduce this.
I see.
Thanks.
And the second question is related to, so it's not got me, is the code book trained together with the model or is something that you decide a priori?
So here, the code book is training together with the model if the entry gets looked up. So by this mechanism here, we are also, so there's the normal translation loss, and
Mhm.
this will be also activated onto these entries here. If any of these entries become looked up, and then they will also update along with the model, with the translation model.
I see.
Yeah.
So, and K, I imagine is smaller than the normal size, right? So you want to reduce also the dimension of the vector you pass to the decoder. So here,
Um, the number of entries, so we actually tuned it a little bit. So I think we did like 1,000 entries, 10,000 entries, 5,000, like 1,000, 5,000, 10,000. We ended up with the 10,000. It's also a bit performance related. So
yeah, yeah,
in order to be comparable to other methods in terms of the translation performance.
yeah. Okay. So thanks a lot. Thank you so much.
Thank
Sorry
you.
for interrupting you.
No, 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 it's all good. Anybody else, if you have questions, please do ask. It's nice to clarify
Can I
this
please have a
already.
quick question? Can I please have a quick question?
Yeah.
So can you please go back to the previous slide?
Yeah.
My question is, the main one, the main figure. Yes.
Yeah.
So my question is also related to K. So
Mhm.
wonder what's your intuition on why 10,000 when K is 10,000 works the best? Why when K is smaller, for example 1,000 or 100,000, they are not working as good as 10,000?
Yeah, thanks for the question. So I guess what I could tell from the empirical evidence of tuning this K is that when there's a smaller amount, so if we use 1,000, the eventual translation performance isn't as great it's maybe losing 2 or 3 blue points or something. It's still doing translation, but I guess it's very much related to the bottleneck. I mean, the more entries we have, the more we could represent by the discretization module. So I guess a smaller size would mean that we are really restricting the number of varieties what we can represent there. Scale, I actually didn't scale up to like 100,000 because I mean this is just like a word embedding table. So 100,000 of vocabulary itself, it's already a big memory amount. And also when doing the nearest neighbor lookup, we have to consider the pairwise distance. So a bigger K also means that we have to store a lot of entries for calculating the distance. So I actually didn't scale up to that high. In short, how I determined this in the end was to have, I stopped when having comparable performance to the baseline. I hope that answered the question.
Sure. Thanks for your answer.
Thank you.
Yeah, I also have a question about randomly accessing either the discretized or the continuous context. So do you mean at the token level or at the utterance level? So is it?
So it's at a sentence level. I'm not like
So it's the whole sentence that you either access continuously or.
Yes.
Yeah, and then so is it a? So I assume this is an attention mechanism from the decoder onto either the continuous or the the continuous representation of the discretized context. So is it a different? Is it attending to a different stream, or is it attending to the same stream? So does it imply that you want the continuous representation of the discretized context? Is that supposed to be close then to the continuous context?
I'm not sure if I got everything, but I guess if you were asking about what kind of context the decoder was able to access, then I would say there's basically this coin flip. Sometimes it sees the more the continuous one, and sometimes it sees the discretized one.
But is it the same? So do you have only one attention mechanism in the decoder?
Yes.
But do you have two attention mechanisms, one for the continuous stream and one for the continuous representation of the discretized stream?
Okay, I see. Thank you for clarifying. So there's just one mechanism. There's just one encoder decoder attention. So what differs is that by the coin flip,
it's either
the encoder context is different. Either it's the orange thing or the blue thing.
Yeah. Okay. Thank you.
Thank you. All right. Thanks everybody for asking questions. And now I'll quickly go over the experiment setup. So to put our approaches to test, we actually reused some data from shared task that we participated in last year from WMT 2021, the large-scale multilingual shared task. And we focus on the track with Southeast Asian languages. So there's Malay, Javanese, and Filipino. And there we also have different bridge languages. So one is English. There you see we have parallel data that is more or less 2 million to 12 million sentences. And between all these Southeast Asian languages, we'll then try to do zero shot. Another similar setup that is with Indonesian in the bridge. The general data setup looks similar, but I guess in general, because of the resources, we don't have as many sentences as before. It's roughly a quarter of before in terms of the sentence amount. And we are initializing our models by the pre-trained MM100. It's released as part of the resources for that shared task. I have to point out that this pre-trained model actually covers the zero-shot directions that we consider here. So the assumption here is that we want to use the pre-trained models as a form of resources, but without accessing or without assuming that we have access to all its training data. We also compared to two kind of popular ways of encouraging language independent representations. The first approach is the language independent objective. So the idea there is that the source and target sentences, they have the same meaning, so they should be represented similarly. What happens there is that we have an additional loss that reduces the difference between the encoded source and target sentence. And the other approach is the adversarial language classifier. So the idea there is that if the encoder representation is language independent, then there should be very little signal about the source language. So there's this adversarial language classifier on top of the encoder, sort of to debias the encoder output from its language signal. Right. All right. When reporting the results, we are using SPBlue, following the evaluation protocol from the shared task last year. And we aggregate the results this way. So there are supervised directions translating into and out of the bridge language. And then among the Southeast Asian languages, it's zero shot. First, looking at the English bridge setup, this is the performance of decoding the pre-trained model out of the box. So since this model has like over 10,000, no, 100,000 directions to specialize in. No, actually 10,000. I'm sorry. There's also quite some distraction, I would say. So on these lower resource directions, it's not the performance isn't super great. But then if we continue training again on our directions of interest, so these 6 directions we are interested in, we are able to make the model refocus on this subset of translation directions. However, what is also happening is that it seems to have completely forgotten about the directions that did not have parallel data in the fine-tuning phase. In contrast, if we do the same with the Indonesian bridge setup, what we see is a completely different picture. Here, we're not having the catastrophic forgetting anymore. Instead, the model is still improving on these directions, even though it didn't see parallel data here. So what this means is that the improvements in here in the supervised directions is also bringing the zero-shot direction forward. So this is something interesting that we'll revisit also later. Right. Now let's look at the effect after incorporating our discretization module. The first observation is that, see, here we are gaining quite a bit on zero-shot direction. However, this also comes with some degradation in the supervised directions. So putting all these together seems to suggest that there's kind of a trade-off between the supervised and zero-shot performance. This is with the English bridge data scenario, right? Now, when we go towards the Indonesian bridge one, the picture is different. It seems like we don't have to make such a big trade-off anymore. Instead, we can more or less have a small gain or preservation of performance everywhere. So what this is suggesting is that we can have a much more efficient trade-off between supervised and zero-shot directions. And again, the difference between English and Indonesian bridge we'll revisit later. Now, putting things into context when comparing to the two baselines or to existing models, one is the purple one is the language independent objective, the orange one is the adversarial language classifier. We see that under Indonesian bridge, we are performing on par with them. Actually, here I was happy since we have to limit the capacity by discretization and so on. I was happy to see that. However, when moving over to the English bridge setup, here the figure is wrong. So here is the English bridge data condition. We are actually underperforming the existing models. So one possibility of what happened there is that now the translation directions are all very dissimilar to each other, and therefore our model with the discretization and limited capacity, it's suffering more here. But anyways, let's put things to test a little bit before we make claims. So recall that we earlier said that one good thing about our approach is that we have discrete tokens for the hidden representations, so we could more easily run analysis. That's what we do here. So we extract the discrete tokens for the sentences on a test set that is multi-way. So that means this semantic meanings of all the sentences from different languages are the same. And then we end up with a lot of counts of the tokens, right? And then we normalize this into a distribution. And here we'll be able to compare the overlap of discrete codes between different languages. So on the left, there's the Indonesian bridge set up, the hidden representations for them. On the right, it's the English bridge one. So here we're reporting the KL divergence, where a smaller number means more sharing. I guess the overall trend is that we see there's much lighter spots, so more sharing for the Indonesian bridge case. Of course, in these, excuse me, in these cells on the diagonal, on the left-hand top, you could argue that the higher amount of sharing is maybe related to just more overlap in the raw tokens between Indonesian and the rest of the similar languages. But then for the other cells here, they are identical in the raw inputs. So this is a quite clear sign that actually when we are doing the Indonesian bridge setup, we do have more sharing, not only between the bridge and the rest of the languages, but also overall for the remaining languages in the model. And I think this is a piece of evidence that supports previously the, in general, more favorable results on the Indonesian bridge setup. Right. Now you might ask, okay, we have the English bridge, we have the Indonesian bridge, how about a multi-bridge system? This is also what we tried. We combined the data from the two conditions. And in general, what we are seeing here is that by going multi-bridge, we don't have so big gain anymore on top of the Indonesian bridge. So here we have into the bridge, out of the bridge, zero shot. So when comparing this versus the Indonesian bridge, there's not like a conclusive big gain anymore. Of course, since the English bridge is doing bad, we could see quite a difference. But I guess in general, the takeaway from this part I would like to share is that sometimes choosing a suitable bridge language is at least as important as having a lot of parallel data for training. And what we saw by the analyses as well as the quantitative performance is that if we have a similar language as bridge, then that in general enables more knowledge sharing for the model. And technique-wise, what we presented is a discretization module into transformer-based neural-machine translation, and that helps us to learn somewhat more language-independent representations to improve zero-shot robustness in the experiments. So this is the first part. Is there something that we can really quick clarify?
Yeah, if oh,
Yeah, okay, go ahead.
oh, thanks. Yeah, you observe this different behavior in zero-shot setting between using Indonesian as bridge or English. But if I remember well, the amount of parallel data for those different bridge languages is quite different. So what this catastrophic forgetting, would you observe it as well if, for instance, you had the same amount of data using English as bridge than you have for Indonesian? Do you have such experiment?
So you were asking about in case the data is more evenly distributed, would we still see this?
Let's say that, for instance, for English here, this experiment, you had the same amount of data parallel as what you had for Indonesian. Would you still observe this catastrophic forgetting thing?
Yeah. In other, I don't have experiments on this data setup per se, but in some other data set, I also see this. So what is happening is more related to English being very often on the target. So why this why this number is so low is that, for example, when we ask for zero-shot translate into from Malay to Javanese, it would do English instead. So it's more a problem that the language gets wrong, and in other experiments I didn't see that it's getting better with say different distribution over translation direction, like a data amount from different translation directions. And here, when we train, we also follow this temperature-based sampling. So although here, for example, English Javanese is relatively low, it's getting upsampled to be more represented while training. So here, I think it's really multitask over different translation direction kind of problem instead of data distribution kind of or like data amount kind of problem. I hope that's related to what you were asking.
Yeah, thanks for your answer. I think an interesting complementing experiment would be to subsample the parallel data with English at the same level as the parallel data with Indonesian and check if you still have this catastrophic forgetting behavior.
Yeah, thanks.
Oh, I have a question. Yeah, thank you very much for presentation. So related to the Laurent question, so I'm interested in the similarity of the languages. So I cannot remember what the TL means, but Japanese and Malaysian and Indonesian belong to the same language group.
Yeah.
So yeah, apparently the English is different. So I think the having the Indonesian as a pivot language for MSTL Japanese are better. So if you control the training data as Laurent suggested, so how much this language similarity affects to this framework?
Yeah.
So I would like to know, but you don't have a result now. So maybe in future, please let us know.
So this is an interesting question. So definitely Indonesian is more similar to Malay, Javanese, and Filipino. English is different in several ways, I guess. The biggest, the most surface level is the lexical difference, I guess. If I look into the data, Indonesian has a lot of shared words with Malay and the rest. I guess there's another difference that is the structural level, so word order, and so that this would be a bit more difficult for me to see.
I think word orders are very similar.
Okay. I mean, I don't know any of these languages, so it's hard.
Maybe Sakuryani is here, so you can say something like that.
Yeah, so actually Indonesian and Malay is actually come from the same language, but they just grown up a little bit. So they are maybe 80% is the same. So if you use Indonesian as a bridge language, I don't think that the Malay Javanese is become zero shot, because you already learned so much from the Indonesian. And also, like, is it your translation based on the character base or word base?
It's based on BPE, so I use the same vocabulary as the MM 124 that was released as part of the shared task.
Okay, yeah, so that one is also because Japanese and Indonesian, even like the word is different, some of the subword is similar. So just like different the last one or things like that. So then if you use BPE, then many like similar, like sequence of those subword is also the same. And
Yeah.
also so I also, before working on the Indonesian Filipino, is also like many similar support. So yeah, that's why I think it's already learned the sequence from that one.
Yeah. Thanks for the insights. So actually, I think this is more or less agreeing with this observation here, where we see more similarity between Indonesian and the rest. But what I found interesting is also among the other languages that are not connected to, like, comparing languages without the bridge, because here what this is showing is that even given the same input, if we train a model with Indonesian bridge, it's better for sharing than training with English bridge. So I think in general, it's kind of agreeing with like linguistic knowledge, but for me it's still interesting to see this block of difference here. So yeah, thanks for sharing the linguistic knowledge.
I have a question actually.
Okay, there was a question also by Barry. If you can go, Sakti, and then we move to Barry.
Hi. Oh, sorry, I was just trying to get my camera on. Yeah, thanks for very interesting talk. I mean, it kind of connects with what was just said there. Okay, so you've made a conclusion about language similarity, but I mean, my sort of experience of multilingual MT is that there's just a massive number of confounding factors. And I'm not familiar with this data set, but just what we're hearing here and just thinking about the languages involved, there's problems that we come across. For example, we know that language identification doesn't work very well for low resource languages.
Right.
So there's often accidental mixtures in the data creation. Perhaps there's code switching. I don't know enough to know whether there's code switching going on. So there's domain effects. So in terms of saying something about language similarity, okay, so we know that English is different from the other three languages. But whether what you're seeing is about some language similarity in some typological and linguistic sense, or whether it's about other data related factors, I'm kind of less clear about that. So just, I suppose if you wanted to make a strong claim about language similarity, you'd probably need to test on some other sets of languages before you can make that kind of claim. Yeah, just to note that there's these many confounding factors in multilingual MT that are really difficult to control.
Right. Thanks for the remark. I fully agree. Here, if I may make a last remark on the data set, it probably is one of those setups with a lot of confounding factor, because in that shared task, basically what was released was a lot of data out of the Opus platform. So it's domain mixed. It's also probably with bad lang ID, although we did clean up in the pre-processing, but it's not gonna remove everything. So yeah, I fully get the point that we could make a stronger claim if we have some additional experiments supporting this. Thanks.
Sakti, sorry for interrupting you before.
Yeah, it's okay. So I might miss something, but as you already used the bridge language, so why you still use kind of like artificial language for your code book? I mean, how about if you use like those from those bridge language will.
So here are, for example, this line is the pivoting. So this would mean that the performance of translating into English and out of English again. So sadly, we are not beating pivoting over the intermediate language still, but at least when we started out on this project, the motivation is that we wanted to get closer to pivoting, and I mean, indeed we do get closer, but we are still not beating the condition of pivoting in and out. I guess
Okay.
a downside theoretically of pivoting is that we're potentially losing information by say going through a third language, but again, there are many other things that that need to be improved before we could get to a point where we can say declare war on pivoting performance.
Okay, thank you.
Thank you. Thank you everybody for nice questions. Then I'm gonna move on to the second part. This will be a bit shorter than the first, so we should be good still on time. Right, so the second part is about reducing the modality difference between text and audio. Right, so far we talked about trying to learn language independent representations for text-to-text translation, where we try to have some higher resource directions helping other directions without so much parallel data. So in end-to-end speech translation, there is also a very similar or analogous situation where we have data scarcity with directly paired speech translation data, but we do have often more data for transcribing or machine translation. So there, what we tried to investigate is how to learn some representation that is more modality independent, and how, if we can do that, to take advantage of the higher resource tasks like ASR and MT. Right. So what we do there is, excuse me, is that we first train a model that is multitasking over ASR and MT. So here we have shared upper layers of the encoder and also the whole decoder. We do reserve more layers for audio with the motivation that for encoding audio, we have to probably learn more complex mapping from the raw speech signals. And then we'll be training multitask with ASR data and MT data. Optionally, in order to bring the two modality closer, in the sense that having a more similar representation for audio and for text, we additionally have this similarity loss between the audio and text representation of the same sentence. So in detail, what happens is that we mean pool the encoded representation and then reduce the distance between the audio and the text representation. So overall, this should be lowercase. Overall, the model is trying to reduce the error on ASR, on MT, and also trying to reduce the similarity loss. Now, after we have this, we'll do fine tuning on direct speech translation data. Here we'll just take the model that was trained from before and continue training with a fraction of the available end-to-end speech translation data. And this is basically to simulate the low resource scenario. Right. Now we have some performance scores on CoVoS T2, English to German. We are reporting blue scores here, and we'll consider like 10% or 25% of the available end-to-end speech translation data. So the full amount is roughly 120 hours of end-to-end data. So here this is like 10 hours or something. Starting off, as we can see, directly training a model like this doesn't work. I mean, training end-to-end models with full data amount is already challenging at times, but here what is showing is that it's even more challenging under low resource. Here now, when we additionally do this pre-training with ASR or pre-training with both ASR and machine translation, we see that we can progressively get a little bit higher performance. And lastly, we see that if we also have that similarity loss, kind of enforcing similarity between audio and text in the pre-training phase, we get even further gains. And for the context, if we do 100% of the end-to-end data, then the blue score is around 14.9. So here, although the scores are kind of low, it's not super far from the condition of having full data. We also analyzed a little bit, are we actually bringing the, excuse me, are we actually bringing the two modalities closer? To investigate this, what we do is that we add a classifier on top of the encoder to classify for modality. So on each of on a frame or token level, we have a binary classifier classifying for, is it audio input or is it text input? Of course, this is with a trained model where the rest of the parameters are frozen. So here, if we look at the result, we are reporting here for the accuracy on the audio input and the accuracy on the text input. And if we do this base multitask model without any similarity loss, it's quite clear that the two modalities are very distinct. It's nearly always possible to distinguish what is what. On the other hand, after introducing the similarity loss, enforcing cross-modality similarity, we see that at least for the text input, there's quite a bit of confusion on whether it's actually audio or text. So this is kind of in a way supporting the evidence that we are actually gaining by having a higher amount of similarity between the modalities.
Sorry, I have a quick question.
Yeah, go ahead.
Why you see only on the text and not on the audio? Why the audio remain the same?
So one thing is it's a classifier that is trained jointly, so it's a bit imbalanced because there are many more frames for audio than for text. So it's kind of always incentivized to get more correct on the majority. So yeah, thanks for the question.
Yeah, thanks.
Right. So I guess the quick takeaway from this part of the talk is that we see some evidence that we could improve end-to-end speech translation performance in low resource conditions. and we could, but by introducing some higher similarity between the text and audio modality, and modeling wise, we introduced a multitask model that handles both audio and text inputs, and that is an approach that allows us to leverage the ASR and MT data. Right. So before questions, I want to advertise that we also have code for the first part as well as our baselines. Please feel free to use that. The second part is mostly done by my colleague Tuan. Now, if you have questions, please feel free to shoot.
Yeah, so first of all, thanks a lot for the presentation, Danny. Very nice, very interesting works. So do you have any question for Danny?
Can I have a question, Danny?
Go ahead, go ahead.
Thanks for the presentation. Can you please go back to page slide 25?
This one?
Yes. So I understand in this work, your main focus is on low resource conditions, but just out of curiosity, have you ever done ablation study on 100% data condition where you remove this similarity loss? I wonder in that case whether what's the gap like, whether it's a significant or it's not.
I see, I see. So here, we do have one, we do have one data point for just like fine tuning on the so this is without the similarity loss. So this is what happens when we have 100% of the end-to-end data. In general, what we see is that like in lower resource, like in the 10% condition, we do have more gains, but it's also probably because the starting point is kind of weak. So when we have more and more data, the gain kind of gets less. So I guess it's in a way showing that this is working more in lower resource conditions. I hope that more or less covers what you were asking.
Sure. Yeah, thanks for your answer.
Do we have any other questions for Danny?
Maybe. Oh yeah, go ahead, Barry.
Oh, it was just a quick clarification on this slide. When you're adding the pre-training and the similarity, you're not adding any extra data, are you? Apart from perhaps the transcriptions, but there's no extra data.
No, there's the fine-tuning phase is the same. So this phase is the same. The only difference is that whether so ASR would be only training the base model with this. Both would be training with both ASR and MT. Then with similarity loss would be additionally with ASR, MT, and the similarity.
Sure. Okay, but it's the same data set.
Yeah.
Yeah, thanks.
Thank you.
Laurent?
Yeah. Did you try to have a similarity loss that is not only between the last layer of the text encoder and the last layer of the speech encoder, but which involves maybe more layers, so like the n last layers, for instance, of both audio and text encoder? In order to enforce this to be a bit more similar, not only at the last layer, but maybe a bit more.
Yeah, it's an interesting idea. We didn't try that. I guess, yeah, it could make sense to add a few more. But I guess our motivation for having it on top was this is what's gonna be the encoder output is gonna be what's fed for the decoder. Yes. But it would be interesting
maybe
to try out.
it will be a bit easier to train, and I don't know about efficiency, but
yeah, interesting. Thanks for pointing this out.
I have a question. Can I make
Please,
a question?
Please.
So on this slide, yes, I have a question. Very interesting. But if you train the encoder of the text encoder first, and use this text encoder to the audio encoder, and then freeze the text encoder part, and then only tune the audio encoder layer 1 to 20, what happens? Because this is more straightforward, no?
I'm actually not sure what it's a bit speculative. I don't know how the performance would compare to the current setup.
Yeah, what we want to do is to make a same parameter for the text encoder, and so yeah, text encoder part can be trained first, and then on the audio encoder part, the initial layer from 1 to 20 to include the audio encoder part and also difference of the text encoder part from the speech. Then I think this may be more learnable than similarity loss. So maybe I think it's nice to see a difference between two ideas.
Yeah,
that's just a comment.
Yeah, this is an interesting idea because I do agree that in our case, when we do the similarity loss, it's kind of the assumption here is that we want to push the audio and the text like to some middle ground, but if we want to, if we say like, okay, our text encoder is already really good, we now want to push the audio towards the text, then it's, I think actually there was some paper maybe from Meta that did this. I'm not sure anymore.
Yeah, kind of traditional way, but
oh,
it's
okay.
nice to see difference. Yes.
Thank you for the remark.
So do you have any other questions? Okay, so thanks a lot, Dan, for the nice presentation. And I have a couple of announcements before closing. So we have been, so as a SIG, we submit a special section request, Interspeech 2023, and we have been informed today that this has been accepted. So we circulate a bit more information about this in the SIG main list, and we hope to see a lot of papers this special section. So the last things I'd like to wish you Merry Christmas to you and to your family, and have a nice break, and see you next year with more and more seminar. Thanks everyone for attending today. Enjoy your holidays.
Thank you.
Thanks a lot.
Thank
Bye.
you.
All the
Bye.
best for the new year.
Thanks to Danny for a very nice